Now, to prove trigonometric identities, there's a few things you've got to keep in mind. Because it's a proof that you're making, you need to start with either the left-hand side or the right-hand side and then basically just rearrange it. Now, you've got a bunch of ways that you can rearrange it. You can use your ratio identities, your reciprocal identities, the complementary ones, or the Pythagorean ones. You can also use any other equation solving techniques that you know, such as factorising or expanding. But we want to keep on going until it looks equal to the other side, at which point we state that it equals the right-hand side if we started with the left or vice versa. Now, you don't want to balance it like it's an equation, so don't add or subtract things to both sides. And you don't need to attempt to solve it for theta, all right? Because what we're doing is we're proving that something is true. Now, let me give you an example of why you don't want to balance it. You're taking an identity and saying that whole thing on one side of the equation is equal to the whole thing on the other. And so you need to treat them separately so that you can say, well, I've got all of this and it's equal to all of that. Now, to give you a super simple example of what we don't want to do and what we do want to do, imagine if I asked you to prove, say, that 4 minus 1 was equal to 3. Now, we know that that's true, all right? But to set out the proof nicely, what you'd do is you'd say the left-hand side is equal to 4 minus 1, and that is equal to 3, and that is equal to the right-hand side. So with a proof, you sort of have an input and an output, and in between you've got your equal signs under each other, and you've got a bunch of statements that are all true all the way down. So you're actually proving that that entire left-hand side is equal to the entire right-hand side as they were given. If you were to try and balance that equation and say, well, let's just add 1 to each side, your first line would be to say 4 equals 4. Now, that's true, and you could therefore say, there you go, it's true, but it's a really clunky way to set out a proof, and it doesn't actually prove that this is equal to that. It just proves two things that are not actually what was asked. Does that sort of make sense? So, start with the left or the right. Now, which do you start with? Start with the one that gives you something to do, to rearrange it. If I started with 3 on this really simple example, there's so many things I could say 3 is equal to. I could say, all right, the right-hand side was 3, and that's the same as, I don't know, lots of things. It's the same as 3 ones, it's the same as all kinds of things that are not 4 minus 1. The reason I wanted to start with 4 minus 1 is it gives me something to do. It gives me a way to rearrange that. And then the answer just dropped out. When you're proving a trigonometric identity, you need to decide which side you're going to start with. And looking at one like this, I'm thinking I should start with the left-hand side, basically because I can see there's brackets there that I can expand. So it sort of gives me something that I can easily do. And that makes me feel like I've got direction going forwards. If I was to start with the right-hand side, there's lots of things that I could say sine squared theta are equal to. I could make that equal to its reciprocal ratio or its complementary ratio, but that wouldn't help me get to this side. So I'm going to start with the side that gives you purpose, if you like. Left-hand side equals, now I can see I've got the difference of 2 squares here because we've got 1s and I've got cos thetas with a plus and a minus. So that tells me to expand that. I do 1 minus cos theta all squared, which remember we write like that. Now at this point, have a look at where you're going and you'll probably go, hey, I can see what I need to get there. This is going to be one of those Pythagorean identities. Now at that point, it's not a bad idea to write down the identity that you're thinking of over here. Sine squared theta plus cos squared theta equals 1. That's something that you know. All right. So if you've got 1 minus cos squared theta, well, how do you build that? Obviously by subtracting cos squared theta from both sides of this equation. So that would give you this line, sine squared theta equals 1 minus cos squared theta. Now, if that's true, and you've got 1 minus cos squared theta, which is this, then that's going to be equal to sine squared theta, okay? Now at this point you've made it to the other side, so you say that's equal to the right-hand side. Now if going from one line to the next is something really simple and quite obvious, you don't need to put in your proof how you got there. But as you're learning to do these, I would recommend this bit of working over here. You can even put it in a box to make it look a little bit separate but sort of part of your proof. It's showing your thinking over on the side, but it's also making sure that you don't mess up. And the more you practice doing this, the more you'll get familiar with the fact that you can change this identity to make it look like that. Now, when you're doing these questions, there's a bit of flexibility in how you do them. So have a look at the question before you start and plan some sort of action. Looking at this side looks a little bit nasty, and I've got things multiplied by each other. As soon as I see these squares here, I think, can I use that in one of those Pythagorean identities? And most of those identities have things added together. So the fact that we've got some adding happening over here and multiplying happening over here, I have no doubt that I will be able to prove this, but I'm thinking I should start with this side because there's something I can do straight away. Now, how do I know what to do? Well, I'm adding fractions, and when you add fractions, there's common things that you know you need to make common denominators, and that'll change the form of it. So I'm thinking I'll start with the left-hand side here. Now, if you've started with the side and you just end up in a whole world of hurt and feel like you're not getting to the other side, sometimes it makes sense to go back, start with the other side, and see if it works better the other way. You'll get the hang of these the more of them you try. Now, the left-hand side, we have to just literally rewrite it. Okay, the first thing to do to tidy this up would be to make common denominators. So if I make a common denominator, sine squared theta, cos squared theta, I'm already liking the look of this because it's starting to look a little bit like this. It's got two squared things multiplied together, so I'm thinking it looks good. Now, if I've multiplied this by cos squared theta, I need to multiply the top by cos squared theta. And if I've multiplied this part by sine squared theta, I need to multiply the top by sine squared theta. So that gives me this on the top. All right, next step, have a long hard look at it, see if there's anything you can tidy up. Oh, sine squared theta plus cos squared theta, that's a Pythagorean identity. That equals 1. So on the next line, write that down and rewrite the bottom. Now we've got something that looks a lot like a reciprocal ratio. It looks like basically this would be the same as if I wrote this as 1 over sine squared theta times, I'll just use that as a little dot there, 1 over cos squared theta. I can break it up, can't I? Because if I multiplied these two fractions together, that would just bring the denominators together and I'd still have 1 on the top. But by splitting it up like that, it's much easier for me to see, and of course I know where I'm going, that I can say, hang on, this is the reciprocal of sine, which is cosec, and the reciprocal of cos, which is sec. So that gives me cosec squared theta times sec squared theta. Now I've written them in this order because that's the way I had them there. Sine goes with cosec, cosine goes with sec, and so it makes sense going from this line to this line that it would look like that. At that point though, I can see that that's exactly the same thing as this, they're just switched around the other way. Now I probably don't need to rewrite them like that, that's fairly obvious, so at that point I'm done and I can say that's the same thing as the right hand side. Okay, here we've got a bit more of a tricky one. Which side would you want to start with here? Well, I'm thinking this side because there's more that you can do with it to rearrange it. This side is much more simple, that's something we can aim to get to. So let's just start with left hand side equals sine of theta plus cot theta, cos theta. Now you might be tempted to start fiddling with it already on the first line, but can I recommend that you always write out exactly what the left hand side is, because remember this is a proof. You're laying it out step by step, so it's really important to state exactly what the left hand side is and finish with what the right hand side is. Okay, so sine theta, let's just leave that for the moment and deal with this awkward looking part. Now think cot. We know that tan of theta is sine over cos, so cot is the reciprocal of that. It's cos over sine, isn't it? So let's rewrite this cot theta as cos theta over sine theta, and then we're multiplying that by cos theta. Okay? Now, if you wanted to, you could say, hey, cos theta times cos theta, that's cos squared theta, and do that on that line. I'm going to write that down on the next line. Now, it's up to you exactly how much you do on each line, but what you're really aiming for is to make your proof really straightforward so that nobody reading it gets lost and says, hang on, how did you get that? See how by keeping that separate, you can see the cos goes from there to there and the cot just changes. So it's really easy to follow. Okay, what are we going to do next? Well, we're adding two things together and we want to get one term. So if I'm adding something and I've got fractions here, making common denominators makes sense. So sine theta is really sine theta over 1, if I put this fraction so that it's over sine theta, then I'm multiplying the denominator by sine theta. So to make up for it, I need to multiply the numerator by sine theta as well. So that would give me sine squared theta over sine theta plus cos squared theta over sine theta. Now they're both over sine theta at this point, so it's probably not too much of a stretch to do those two things together and see that if I'm adding together two fractions and they both have the same denominator, I can just put that denominator down the bottom once. All right, this is looking good now because I've got sine squared theta plus cos squared theta, and I know that that equals 1. So I have 1 over sine theta. At this point you start getting excited because you can see that you're just about there. That is the same as cosec theta, which is the same as the right-hand side. And you're done.